What does it take for a single aircraft to forever change how we fly? 10 planes answered that question, and the first did it at nearly 7 times the speed of sound, its skin glowing white-hot at the edge of space. How do you control an aircraft when the atmosphere is too thin for wings to work? The rocket-powered North American X-15 was built to find out. Dropping from a B-52 carrier plane on June 8, 1959, the X-15 pushed piloted flight into hypersonic territory where conventional aerodynamics vanished. Flying near the edge of space, pilots relied on thrusters to maintain attitude, enduring blinding plasma sheaths and intense physical strain. Reaching a peak altitude of 354,200 feet, the program earned 8 pilots their astronaut wings. It remains the fastest piloted aircraft in history, proving that humans could fly safely into the upper atmosphere and return. How do you transition hypersonic speed from a laboratory experiment into a daily operational reality? In 1964, Lockheed's Skunk Works answered with the SR-71 Blackbird. Designed to cruise above 85,000 feet at Mach 3.2, the Blackbird relied on speed as its primary defense, easily outrunning surface-to-air missiles. To survive the intense aerodynamic heat, Lockheed built 93% of the airframe from titanium. But this created a severe manufacturing obstacle. Standard steel tools contaminated the metal, forcing engineers to invent entirely new machining methods and custom hand tools just to shape the titanium. Did this struggle to master a volatile metal permanently reshape how modern aerospace components are built? How do you rewrite the rules of aerial combat when your industry is crumbling under Allied bombs? In April 1944, the Messerschmitt Me 262 entered Luftwaffe service as the world's first operational jet fighter. On July 25th, it intercepted a British Mosquito over Munich, demonstrating a speed advantage of 100 miles per hour over piston aircraft. Yet, this technological leap arrived without the necessary infrastructure. Chronic fuel shortages, disrupted production lines, and inadequate pilot training neutralized its battlefield impact. Can a revolutionary design reshape history when the system built to support it has already collapsed? How do you transition supersonic flight from military secrecy into a regular passenger experience? In 1969, the Aerospatiale BAC Concorde answered by cruising at Mach 2.04, having transatlantic travel times. To land this needle-like airframe safely, engineers designed a drooping nose that pivoted downward so pilots could see the runway. Inside, an advanced analog, fly-by-wire system constantly adjusted hydraulic controls to maintain stability at twice the speed of sound. Yet, extreme fuel consumption and strict sonic boom regulations ultimately restricted Concorde to premium oceanic routes. Did this engineering masterpiece prove that technical triumph cannot always overcome the hard realities of economics? How do you turn flight from an elite adventure into a practical, everyday business? On February 8, 1933, the Boeing 247 took flight, debuting an all-metal semi-monocoque fuselage, retractable gear, and variable pitch propellers. It set the blueprint for modern airliners, though its 10-seat capacity limited its commercial run. To bridge the gap to the jet age, the Vickers Viscount made its first flight on July 16, 1948. Powered by 4 Rolls-Royce Dart turboprop engines, it gave passengers a quiet, pressurized cabin with signature oval windows, proving that operating economy and comfort could drive out older piston fleets. Did these practical passenger workhorses do more to democratize the skies than the most exotic record breakers ever could? How do you conquer the silent upper atmosphere when the very air pressure keeping passengers alive is slowly tearing your airframe apart? On July 27, 1949, the de Havilland Comet flew as the world's first commercial jet airliner, offering unprecedented speed and comfort. But by 1954, catastrophic mid-air breakups grounded the fleet. Royal Aircraft Establishment investigators submerged a complete fuselage in a pressurized water tank, cycling the cabin structure until the metal ruptured. They found that stress concentrated around the square windows, causing microscopic fatigue cracks to spread. Did this structural failure do more to build a culture of safety than any flawless flight ever could? How do you protect a strategic bomber when speed alone is no longer enough to outrun modern air defenses? On July 17, 1989, the Northrop B-2 Spirit made its first flight, replacing the pursuit of extreme velocity with the power of invisibility. Its radical flying wing design, measuring 172 feet across, eliminated the vertical tail surfaces that reflect radar. Instead of adding stealth as an afterthought, the bomber's entire shape became its shield, reducing its radar cross-section to that of a bird. Capable of flying over 6,000 miles without refueling, the B-2 proved that absence from radar is the ultimate strategic advantage. In a world where detection means destruction, does the ability to remain unseen make this the most revolutionary aircraft ever built? How do you build a machine that doesn't just slice through the air, but uses its own supersonic shockwaves to stay aloft? On September 21, 1964, the North American XB-70 Valkyrie took flight, designed to cruise at Mach 3.1 at 70,000 feet. To survive this extreme environment, the massive delta-winged bomber utilized compression lift. By lowering its folding wingtips, the Valkyrie trapped its own high-pressure shockwave beneath the fuselage, riding the airflow like a surfboard on a wave. Did this experimental giant mark the absolute physical limit of pure aerodynamic engineering? How do you force an aircraft to fly when its wings are swept forward, making it inherently unstable? On December 14, 1984, the Grumman X-29 made its first flight, featuring forward-swept wings that generated high lift but also intense structural twisting. No human pilot could manually keep this design stable. The real control came from the software, a triple redundant digital flight control system making 40 adjustments per second to prevent the airframe from ripping apart. The X-29 proved that an unstable airframe could be made safe through code. Did this shift the focus of aviation from physical geometry to digital logic? Today, these breakthroughs define our skies. Yet, as we enter the era of autonomous flight, the frontier is shifting. What will the next revolution look like?